This is the EdExcel AS Level Maths Paper 2, covering the Mechanics module, and this is from the 2024 series. Question number 1. Figure 1 shows the speed-time graph for the journey of a car moving in a long queue of traffic on a straight horizontal road. At time t equals 0, the car is at rest at the point A. The car then accelerates uniformly for 5 seconds until it reaches a speed of 5 meters per second. For the next 15 seconds, the car travels at a constant speed of 5 meters per second. The car then decelerates uniformly until it comes to rest at the point B. The total journey time is 30 seconds. So the below information is summarized in figure 1. From 0 to 5 seconds, the car accelerates uniformly with a speed of 5 meters per second. For the next 15 seconds, we have constant speed of 5 meters per second, and then the car decelerates until it comes to rest, and that's in between 20 seconds and 30 seconds. Part A, find the distance AB. The distance AB is found by working out the area under the curve. Now, you'd notice in figure 1 we have 3 segments. We have the segment from 0 to 5 seconds, which is a triangle. We have the segment from 5 to 20 seconds, which is a rectangle. And we have the segment from 20 to 30 seconds, which is a triangle. We have enough information to work out each of those areas. So for part A, the distance AB, that's equal to 1/2 times 5 times 5, which is the area of this triangle, plus 5 times 15, which is the area of this rectangle, plus 1/2 times 5 times 10, which is the area of this triangle. Working this out, 1/2 times 5 times 5, that's 12.5. We add on to this 5 times 15, which is 75, and we add on to this 1/2 times 5 times 10, which is 25. 12.5 plus 75 plus 25, that's equal to 112.5. So the distance AB is equal to 112.5 meters. Part B, sketch a distance time graph for the journey of the car from A to B. In the speed time graph, we have time intervals of 0 to 5 seconds, 5 to 20 seconds, and 20 to 30 seconds. Therefore, in our distance time graph, we will also have the same intervals, 0 to 5 seconds, 5 to 20 seconds, and 20 to 30 seconds. In the first 5 seconds, we travelled a distance of 12.5 meters. And with constant acceleration, that means in the first 5 seconds, with a distance of 12.5 meters, we would have a curved segment such as the one shown here. And the reason it's curved is because we are accelerating uniformly. From 5 to 20 seconds, we travelled a distance of 75 meters, meaning the total distance travelled from 0 to 20 seconds would be 12.5 plus 75, which is 87.5 meters. So from 5 seconds to 20 seconds, we've travelled a distance of 75 meters, and therefore from 0 to 20 seconds, we've travelled a total distance of 87.5 meters. And as we have constant speed for this 15 seconds, we would have a straight line segment from 5 to 20 seconds. From 20 to 30 seconds, we have travelled a distance of 25 meters, and our total distance travelled from 0 to 30 seconds is 112.5 meters. So in total, we have travelled 112.5 meters. And from 20 to 30 seconds, we decelerate uniformly, meaning our line segment from 20 to 30 seconds would be a curve. So here is the completed distance time graph showing the distance from A to B. You can see in 30 seconds we have travelled a total of 112.5 meters. Part A. Find the acceleration of the particle when t equals 4. For part A, let's begin by writing v equals 2t subtract 7 multiplied by square root t plus 6 in an equivalent form. We can write this as v equals 2t subtract 7t to the half plus 6. You will find that t to the 1/2 is the same as the square root of t. To find out what the acceleration is, we need to find a formula in terms of t for the acceleration, and we can do this by differentiating v. And if we differentiate v, a will equal, well, if we differentiate 2t, we end up with 2, and if we differentiate negative 7t to the 1/2, we end up with negative 7t to the negative 1/2 over 2, and if we differentiate 6, we end up with 0. So the acceleration is given by a equals 2 subtract 7t to the 1/2 over 2. So when t equals 4, a will equal 2 subtract, we have here 7 multiplied by 4 to the negative 1/2 over 2. So let's work this out. 2 subtract 7 multiplied by 4 to the negative 1/2 over 2 is equal to 0.25. So the acceleration when t equals 4 is equal to 0.25 meters per second squared. When t equals 1, the particle is at the point x. When t equals 2, the particle is at the point y. Given that the particle does not come to instantaneous rest in the interval 1 to 2, part B, show that xy equals 1/3 multiplied by 41 subtract 28 root 2 meters. For part B, the distance xy will be given by the integral of v between 1 and 2 with respect to t. So xy equals the integral of 2t subtract 7t to the 1/2 plus 6 with respect to t in between 1 and 2. So let's work this out. If we integrate 2t, we end up with t squared. If we integrate negative 7t to the 1/2, we end up with negative 14t to the 3/2 all over 3. And if we integrate 6, we end up with 6t. So we are required to evaluate t squared subtract 14t to the 3/2 all over 3 plus 6t with the limits 1 to 2. So substituting in for our upper limit, we have 2 squared subtract 14 multiplied by 2 to the 3/2 all over 3 plus 6 multiplied by 2. For our lower limit, we have 1 squared subtract 14 multiplied by 1 to the 3/2 all over 3 plus 6 multiplied by 1. Let's work this out. Well, 2 squared, that's 4. And then we have negative 14 multiplied by 2 to the 3/2, which is the same as 2 root 2. And we divide all of this by 3. We add on to this 6 times by 2, so we add on 12. And for our lower limit, we have 1 squared, which is 1, subtract 14 times 1 to the 3/2 over 3, which is the same as 14 over 3, plus 6 times by 1, which is 6. And it turns out we get 7 over 3. So our lower limit comes to 7 over 3. Now, if we evaluate this, 4 plus 12 subtract 7 over 3, that's equal to 41 over 3. And then we have 14 multiplied by 2, which is 28, multiplied by root 2, and then divide all of that by 3. We end up with 28 root 2 over 3. So we have 41 over 3 subtract 28 root 2 over 3. And if I factorize out a 1/3, we have 1/3 multiplied by 41 subtract 28 root 2. So the distance xy is given by 1/3 multiplied by 41 subtract 28 root 2 meters. Question 3. In this question, I and j are perpendicular unit vectors in a horizontal plane. A particle P is moving on a smooth horizontal surface under the action of 2 forces. Given that the mass of P is 2 kilograms, the 2 forces are 2I plus 4j newtons and Ci subtract 2j newtons, where C is a constant. The magnitude of the acceleration of P is root 5 meters per second squared. We have to find the 2 possible values of C. To begin with, let's find the resultant force F The resultant force F is the sum of this force, 2I plus 4J newtons, added to this force, Ci subtract 2J newtons. And in terms of our I's, we have a total of 2 plus C of them, and in terms of our J's, we have a total of 2 of them. So, the resultant force F is equal to 2 plus C I plus 2J. We've been given the mass, we've been given the magnitude of the acceleration of P, and therefore, using Newton's second law, F equals ma, we have F, which we've just found to be 2 plus C I plus 2J, equaling 2, the mass, multiplied by the acceleration vector A. If we divide through by 2, we can find the acceleration vector. You will find the acceleration vector to equal 1 plus a half C I plus 1J. And therefore, the magnitude of the acceleration will be given by 1 plus a half C all squared plus 1 squared square rooted. So, knowing the magnitude of the acceleration of P is root 5 meters per second squared, we can set this equal to root 5. So we have the square root of 1 plus 1 half C squared plus 1 squared equaling root 5. To find C, we need to solve this equation, and to begin with, let's square both sides to get rid of this square root. And if we do that, we have 1 plus 1 half C squared plus 1 squared equals 5. If I subtract 1 squared from both sides, we end up with 1 plus 1 half C squared equals 4. And if we square root both sides, we have 1 plus 1 half C equaling plus minus 2. And therefore, we have a solution C equals 2. We have another solution C equals 6. Hence, the two possible values of C are C equals 2, C equals 6. Question number 4. Figure 2 shows a car towing a trailer along a straight horizontal road. The mass of the car is 800 kilograms, shown here, and the mass of the trailer is 600 kilograms, shown here. The trailer is attached to the car by a tow bar which is parallel to the road and parallel to the direction of motion of the car and the trailer. The tow bar is modelled as a light rod. The resistance to the motion of the car is modelled as a constant force of magnitude 400 newtons, as shown here. The resistance to the motion of the trailer is modelled as a constant force of magnitude R newtons, as shown here. The engine of the car is producing a constant driving force that is horizontal and of magnitude 1740 newtons, as shown here. The acceleration of the car is 0.6 meters per second squared, and the tension in the tow bar is T newtons, as shown here. So in figure 2 we have shown the forces acting on the system. Using the model for part A, show that R equals 500. To find out what R is, we can use F equals ma for the whole system. And if we take a look at the whole system, we have a forward force of 1740. We have a resistive force to the car of 400. We have a resistive force to the trailer of R. And the resistive force of T from the car and the forward force of T from the trailer simplify to 0. And we know the mass of the trailer and the car. Hence, we have 1740 subtract 400 subtract R equals the total mass, which is 600 plus 800 multiplied by the acceleration, which we know is 0.6 meters per second squared. So we multiply by 0.6. So we have 1740 subtract 400 subtract the 600 plus the 800 multiplied by 0.6, and it turns out we get 500, meaning R is equal to 500. Part B, find the value of T. For part B, to find the value of T, we can consider F equals ma, but for the trailer. For the trailer, we have a forward force of T, a resistive force of R. We know the mass is 600 kilograms. And we know the system is accelerating with acceleration 0.6 meters per second squared. So we have T subtract R equals 600 multiplied by 0.6. We have worked out that R is 500. So we have T subtract 500 equals 600 multiplied by 0.6. Therefore, T will equal 600 multiplied by 0.6 plus 500, and it turns out T is equal to 860. At the instant when the speed of the car and the trailer is 12.5 meters per second, the tow bar breaks. The trailer moves a further distance d meters before coming to rest. The resistance to the motion of the trailer is modelled as a constant force of magnitude 500 newtons. Using the model for part C, show that after the tow bar breaks, the deceleration of the trailer is 5/6 meters per second squared. For part C, if we consider F equals ma, but for the trailer, we know the trailer has just a resistive force of 500 newtons, so we have negative 500 equals the mass 600 multiplied by the acceleration a, which means the deceleration is negative 5/6 meters per second squared. Part D, find the value of d. Well, we know that the initial speed is 12.5 meters per second. We know when the tow bar breaks, the trailer moves a further distance d meters, that's what we're finding. We know the final speed is 0 meters per second because it comes to rest. We know the deceleration of the trailer is 5/6 meters per second squared. Hence, what connects those is v squared equals u squared plus 2as. So we have v squared, that's 0 squared, equals u squared, that's 12.5 squared, plus 2as, so we add on 2 multiplied by a, which is negative 5 over 6, multiplied by s, which in this case is d. And we are required to find d. So, d is equal to 12.5 squared divided by 2 times by 5 over 6. And it turns out d is equal to 93.75. In reality, the distance d meters is likely to be different from the answer found in Part D. Part E give 2 different reasons why this is the case. Well, the first reason is resistance to motion of the trailer will not be exactly 500 newtons. The second reason is the model takes no account of forces acting side to side.